My name is Campilho. I come from ISEP in Portugal, and I'm presenting a work on the experimental and numerical analysis of sandwich structure. In this case, it is 3 and 4-point bending, although the title only mentions 4-point bending. And we are going to use different types of damage models to evaluate the skin, the core, and the adhesive. Here we can see the layout of the presentation. After the objectives, we will make a short introduction to sandwich structure and numerical modeling. This work has included an experimental campaign regarding the fabrication of the sandwich structure and testing and data analysis, followed by a numerical work carried out in Abacus software and with all of the respective comparison between both so that we can validate the procedure. And finally, we will have the conclusion and future work. The main objective of this work is to experimentally and numerically analyze a composite sandwich structure with different skin configurations. In this, we will have hybrid skins between plies of carbon and glass, and also different stacking orientations. To accomplish this objective, run experimental tests in both 3 and 4-point bending so that we are able to obtain the properties and the parameters that we need to validate the numerical technique in terms of failure mode of the sandwich structure. We use the Abacus software to numerically replicate the experimental tests in both 3 and 4-point bending. We want to select also the most suitable damage model to simulate the adhesive, foam, and skin behavior, and finally validate the numerical model so that we can extrapolate this methodology to other types of materials and testing setup. As an introduction to sandwich structures, these are composed of a multi-layer structure that has basically 2 skins and a core in between. There are different materials that you can use for both of these components. Usually the skins are stiffer and stronger so that we can have a higher flexural behavior. In terms of the skins, we can have metal, laminate, wood, laminated wood, and aluminum. And we can also have different types of cores such as expanded materials. In this work in particular, we are going to have a PMI foam. We can also have rivet plates in metal or corrugated plates. We can have wood plates, and finally we can have stretched aluminum, for example, as a honeycomb pattern. In terms of manufacturing method, usually we fabricate the skins by hand layup, by projection molding, by low pressure injection and transference molding, continuous rolling, and then the skin and the core, they are usually connected by adhesive bonding, as we can see, to connect the sheet to the core, which can or not be of honeycomb type. In terms of experimental test campaigns for sandwich structure, there are different tests in the literature that are widespread. We can have tensile tests, lateral compression test, core compression test, which was one particular test that we carried out to the PMI foam. We can have core shear test, and then for the structure we can have bending test, and here we can see an example of a 3-point bending test. In terms of modeling, there are different types of approaches to address the different components of the sandwich. In this case in particular, I just highlighted the ones that we are going to use. The Taiwu iterative criterion for the skins to assess failure of skins, the crushable foam criteria or damage model for the foam, which is the main type of behavior that we identified in the experimental test that we carried out under compression. And then the adhesive layer failure will be tested by cohesive zone modeling. This adhesive was already characterized in terms of strength, in terms of structure properties. And this is the criteria that we're going to use with a triangular damage law. In terms of the work in particular, we are going to consider spins with a hybrid configuration between carbon fiber prepreg and also fiberglass bidirectional prepreg. We are going to test two different configurations between these types of spins. The adhesive is a Force 7710 L100 big component polyurethane structural adhesive from Sika. And as a core, we are going to test the PMI foam from Rocha with reference 71 WF, which will going to be kept constant in all of the analysis. The sandwich design is shown in this figure. We have a core of 10 millimeters, two adhesive layers of 0.2 millimeters, and then we have the skin with roughly 1 millimeter and two different configurations. These configurations, they alternate carbon fiber with glass fiber, and we are going to test two different configurations, although in both cases, the end layers will be always carbon fiber at 0 degrees, which will be the loading direction, the main loading direction, while at the middle we are going to test different arrangements of glass fibers. In one case, plus or minus 45 degrees, and in the second, 90 degrees. Some details about the manufacturing process. The skins were fabricated on the first hand with prepreg layup manual, removal of the air bubbles between consecutive layers, bonding of the prepreg, and repeat the removal of the air bubbles until we have the full laminate with the entire number of plies that we stipulated. With ply film, because the fabrication process will be in a hot plate press, application of a pill ply, overlap of skins, because we are going to fabricate two skins at a time with so we need to overlap them and create the respective barriers, and the curing of the skins in the hot plate press. After having the skins, we can see that we separate the two skins. We cut them to the dimensions, which is roughly 300 by 300 millimeters. We cut the PMI core, and then we start the preparation of the bonding process between the core and the skin. We calculated all of the quantities for each component, because this is the two-part adhesive, so that we can have the right proportion. Some details about the adhesive application and distribution, which was carried out in the skin. After curing, we have the sandwich structure completed, and then we will cut the entire plate in specimens with dimensions so that we can apply the 3-point bending and 4-point bending test. In this slide, we can see the setup for the two types of bending. We have the setup for 3-point bending and also for 4-point bending. We are carrying out this test in accordance with the C393 ASTM standard. So we are using a speed of 5 millimeters per minute, and also the dimensions that we consider according to the standard for the 3-point bending and 4-point bending test. Before the results, in terms of numerical pre-processing, we use the Abacus software, a static analysis, an implicit solver. Initially, we created different partitions in the model. We defined the different constituents, ranging from the core to the skins and passing through the adhesive, which is modeled by cohesive zone elements. And we also considered a higher refinement in the contacting region between the punches and the specimen itself because of the compressive stress concentration that we have at this region. Some details about the computational parameters. Here we can see the incrementation. We have the analysis initially divided into 100 increments, but it is expected as the damage models start to trigger that we have an automatic reduction of the increment size so that we can have the proper convergence of the modeling. Some details about the part interaction. Here we are talking about the specimen and the punches. We consider a normal hard contact behavior to avoid interpenetration, and in here we consider the frictionless tangential behavior so that we try to mimic the roller effect in the specimen. Some details about the boundary conditions. Here we can see that the loading specimens are clamped. These are the lower punches. They are clamped in the reference point of the analytical rigid surface that we consider to model the punches, while the loading punches, they are subjected to a displacement. So this is a displacement control, as in the experiment, of 10 millimeters in the y direction, while we fix the horizontal direction, and we also fix the rotation in the out of plane direction. Details about the meshes and element type. We consider, as mentioned before, a higher refinement in the region of contact between the punches and the specimen, and we consider for the skins and the core a plane strain element with 4 nodes, the CPE4R, and for the adhesive a 4 node also cohesive element with the reference cohesive 2D4 element. In terms of damage, the H.G.E criterion was considered for the cohesive zone model with a triangular law was considered for the adhesive, and the crushable foam damage model was considered for the core of PMI foam. In terms of results, we are going to address one of the configurations at a time. So in this case, we have 3-point bending for skin configuration 1 with the inner plies of glass at plus and minus 45. In this case, we have 2 specimens, experimental and the numerical curve, and we were able to see that between the 3 criteria, the one that triggered failure first was here in the core. So this was the limiting factor, and at this point we have the prediction for the maximum load that we can compare to the 2 experimental specimens that we have in the graphic. The numerical curves are relatively close, and we have an accurate representation of the behavior in terms of the initial stiffness and also the failure load. In this second graph, we have the 3-point bending, but configuration 2. Here we also triggered the core failure in here initially. So we have here our prediction. Here we have a slight higher difference between the experiments and numerical simulation. And now going to the 4-point bending configuration. In configuration 1 for the skin, we also trigger initially the shear core failure in the core, and here we have a numerical value that is in between the 2 predictions for the 2 specimens that we tested experimentally. On the other hand, we have a slightly lower displacement that we observed experimentally. This is the last configuration that we tested, the 4-point bending configuration with skin configuration 2. Here we also had a small underprediction of the maximum load, but a good representation overall of the curve. In terms of skin bending stress and shear stress, we have the comparison of shear stresses and tensile stresses, both numerically and experimentally, and here we can see the relatively error. We have both configuration 1 and configuration 2, and we can see that numerical values are higher than experimental ones in both configurations, up to 15% in the first configuration, and up to 40%, which is significant for configuration 2. This is the same data for the 4-point bending test, and here we can see the numerical values are close to the experimental ones in configuration 1. The maximum error is about 2%, but in configuration 2, we have a higher shear stress value of about 25%. In terms of failure mode, in all of the experimental cases, we had shear failure in the core as the primary failure mode, which agrees with our numerical representation. We can see the shear failure in the core at 45 degrees. This is one specimen for 3-point bending and another specimen for 4-point bending. And here we have the numerical failure mode. Actually, the core which fails at 1.26 megapascal, as it resulted from our experimental testing. We have failure in the core, while the skin and the core, they are not still triggered in terms of complete failure. Here we can see the conclusion. We found out that the orientation of the fiberglass in the skins is not very significant. In the numerical model, we did not observe failure in the adhesive, equally to the experimental test. The skin was also never a critical parameter, but rather we had always failure in the core as we observed both numerically and experimentally. We also have some suggestions for future work, and I would like to conclude my presentation. Thank you so much. And if you have any questions, please feel free to ask me. Thank you.